Hey, today I want to talk to you about how to build privacy-preserving incentive systems with a little bit of crypto. The target audience for this talk is not necessarily crypto experts, but basically anyone with like a rough basic understanding of computer science, I guess. And I will explain all of the things that go into this. Ideally, you come out of this talk thinking, these are like the techniques that these people are using, or this is how they think about this stuff. So let's go for it. All right, we start with what is an incentive system at all. We start with the current state and practice. So I go shopping, I buy my stuff, and then often at the register they ask me, are you participating in our incentive system? If I am, then I basically present such a barcode. They would scan this and then essentially give me a bunch of points. In this case, 7. Why do I do this? Ideally, at some point, I have enough points and I can spend those points on some kind of loyalty reward. Okay. So, in practice, this is realized as follows. Basically, my barcode is just an ID, my personal user ID, and somewhere they have a database of all of the users with all of their point counts. The issue is that every time I go shopping, I also reveal my personal user ID. Okay, so essentially, if they want to, they can also log all of the stuff that I'm buying when I'm buying them. Because every time I'm basically screaming at them, look, this is me, this is Jimothy. Please give me points and potentially take my data. So every time I get new points, they would just update this database. But obviously, this has some privacy implications, which we don't want. Why do stores do this? Well, basically, they want to reward customer loyalty. So basically, come shop at my store, because if you shop here, you will get more and more points and you will get closer and closer to your rewards. So it incentivizes people to shop here. It can also be used to incentivize specific behavior. So if you have a product that people should buy more, you may be able to basically give bonus points for buying this stuff and basically incentivize people to buy more of this particular thing. And then today, obviously, they're also collecting a lot of user data, which has its value. What do we want though? We are crypto people, so we usually want more privacy for people, and that's exactly what we want here. So we want to get rid of this database with all of my buying habits and also the number of points that I have. The provider should not even know how many points I have, like if I'm an active user or like a not active user. Ideally, no information about this. And what we need to do for this is we basically need a new approach, right? Because while I'm still presenting my user ID every time I go shopping to get my points, like none of this will work. Because every time I go shopping, they will see this is this guy and may be able to link data to me. So what we're going to do is we get rid of this presenting the user ID every time, and instead we will do some fancy crypto stuff, basically to make it so that your phone, for example, can store your point count, and there is no need for such a database that stores the number of points that you have. All right. So this is the rough overview of what we want. We want to have this scenario, but with user privacy. And as a starting point, we need some basic crypto stuff for this, nothing too fancy, but we'll start with hashing. Right? What's a hash function? Hash function is, well, a function, we call it h here. It takes some input, and it basically outputs some hash of this input. The hash looks really chaotic. One may say it kind of looks like a random bit string, and this is also what we will do next. So, formally, a hash function maps arbitrary length bit strings to bit strings of length 256, for example. These are publicly well-known functions. So for example, you may know like SHA-2 or SHA-3. Those are like the standard hash functions. So everyone kind of knows the functions. However, they still kind of have this property that they kind of have unpredictable output for new inputs. So if I put in some other input here, the output will have basically no relation to the first input. It will just look like a random bit string again. This is kind of the intuition. So this function is so chaotic that the output looks unpredictable, or is kind of unpredictable and looks random. But how can we model such a thing? Because it's a public, well-known function. So in a way, there is a really easy way to predict what the output of the function will be. To just run the code and evaluate what the function output will be. And ta-da, we know what the output will be. So we need some modeling to kind of encode this property into these functions. So what does it mean that the output is unpredictable? Because, as I said, it's really predictable in a way by just evaluating the function. And what we're doing is we basically assume that that an algorithm that computes h doesn't run the actual code to compute the hash function, but instead interacts with such a magic box like this. What does this magic box do? Basically, it will take the input, what would be the input to the hash function, and it will then actually randomly choose an image, a hash image, it will then randomly choose an image for this pre-image. Okay, so a hash value for this some input. And then it will output this random value. If I put in the same function, if I put in the same input twice, I will get the same output. But if I put in some new input, this magic box will just randomly choose a new output for it. And this way we can model the unpredictability of this function. Because we say algorithms don't actually interact with like the function, with the actual code, but with this magic box that randomly chooses images. And before you put in some input, you won't know what the output will be, because the random choices happen only after you plug it in. That's hash functions. And interestingly, this already suffices to kind of build a very simple incentive system. So let's look at this. The basic idea for these incentive systems will be the user will collect these coins. And a coin consists of two things, an ID and an S. One coin will be worth just 1 point. So if you earn like 200 points, you would just have to get 200 coins. For simplicity for now. The ID of the coin will prevent double spending. So every coin gets a unique ID, and this will allow the provider, the incentive system provider later, to basically check whether this coin has been spent before, whether the coin with this ID has been spent before. And the other thing is the S. This will be what prevents forgeries. So we obviously need to make sure that users can't just come up with their own coins, but they kind of need to actually earn them from the provider. Okay, so very simple setup. The provider chooses a random key k. It's just a random bit string. Then, to earn points, so if I go to the supermarket and I am supposed to get a coin, then I as a customer choose a random ID. Okay, also large bit string. And I send over this ID to the provider. The provider will then hash his key and the ID, and this hash value we'll call S. The coin for the customer in the end is the ID that he chose in the beginning and the S that he got from the provider. Now, the thing that you can immediately see here is that actually the customer cannot compute keys on his own. This is because he doesn't know the hash key k, or the key k. So he won't be able to compute such a value S that's actually the hash of the key and the ID. So this is already like a good property for it. Now, if we spend the coin, we'll do a very simple thing. We'll just reveal the ID and the S of our coin to the provider. The provider will check two things. One, it will take the ID and check its database whether the coin with this ID has already been spent or not. If it has been spent already, then this is like an attempt at double spending. So a user has tried to use the same coin twice, or to spend the same coin twice. And in this case, the provider would just say, no, this is not working for me. You've already spent this coin, you can't do it again. And the second thing that the provider does will check whether this coin is actually valid by checking whether the S kind of fits the ID. So it will again compute this hash value of the key and the ID, and will just check whether S is actually this value. And as I said before, the user can't come up with new coins themselves because they won't be able to compute the correct S for the ID without knowing the key K. Remember, the hash function is this magic box, and without being able to give the right input into the box, you won't know what the output is. You can only guess, but it's like highly unlikely that you happen to guess the correct output for this magic box, or the same output that the magic box also shows that you've never seen. The issue, though, is that this simple protocol has no anonymity. So when I earn points, the user basically just sent over the ID. And now when I'm spending my coin, I also send over the ID. So a malicious provider would basically be able to tell, okay, this coin here that you're spending right now, you earned this 15 days ago while you were buying this and this. So this is something that we don't want to have. We basically want to ensure that the earn transactions and the spend transactions are unlinkable. So the provider shouldn't be able to tell which coin was that I'm spending here, where it was earned. And this is what we will try to get next. But with this approach that we've done, this kind of doesn't work. Good. Let's talk about the basic ideas that we have. We have this simple protocol where we earn points. Now let's think about this. When we're spending coins, we have to kind of reveal the ID of the coin, because this is necessary for double spending. The provider needs to be able to tell, okay, this coin has this ID, and so I can check whether it has been spent before or not. So the thing that we can still do, potentially, is we can hide the ID while we're earning the coin. So we basically just go to the provider and say, I want to earn some coin, but I'm not revealing the ID of the coin that I'm learning. So let's just try something. Basically, we have already seen how to hide stuff. We can use hash functions for this in a way. So let's just try this. The user, to earn points, the user would choose a random ID. And now instead of sending the ID itself, which is what we want to hide, we don't want to send it in plain, the user would send the hash of the ID. Then the provider does what he did before. He would take what he got here and just hash it together with his key, as before, kind of. This kind of works if you think about it. So it's actually true that in this scenario, the hash of the ID hides the ID. So the provider during this earn protocol won't learn what the ID is. Because in order to learn what the ID is, you would kind of have to guess. You would have to guess the ID and then check with the magic box whether this is actually the hash value of it. But now, if we take a look further down the line, if we spend this key, we said we have to reveal the ID, right? And at that point, the provider can just hash the ID and look back at all of the old earn transactions, like this one, and just check whether the ID that we've just sent, whether the hash of it was sent in the first message of this earn protocol. So in a way, we've hidden the ID, but only until we spend the coin. As soon as we spend the coin, the provider can go back and look which earned transaction belongs to the ID. And this is because we have to reveal the ID when we're spending points. More generally, hashing is not that good for hiding things in a, let's say, verifiable way. Because as soon we can hide things like this, but as soon as we reveal or we want someone to check something about a hash value, like this S check here, we have to reveal like the pre-image of it. And at that point, I mean, the provider can just compute the hash value and check whether it has been, where it has been used. So this whole approach with hash functions for hiding things won't actually cut it at all here. We need something more, something cooler maybe. For this, we'll look at more basics, essentially, and I'll introduce you into the world of discrete logarithms. This will be a very short math slide. We'll have a group G. Any group, reminder for you, a group is basically a set of values, and it has a multiplication operation and an inversion operation. You can think about like the real numbers without zero as a group, but don't, because ours kind of look different. The size of our groups is a prime number. Okay, so there are p many group elements in this group. Because it is prime order, every element is actually a generator, except for the one element. And the important thing will be that if I take a random exponent, so exponents I can think of as living in ZP for technical reasons, I guess. If I take a random exponent and raise some group element to this exponent, to the power of this exponent, then the result is uniformly random in the group. This is the important property that you need to remember. So random exponent, raise group element to this, then the output is uniformly random and kind of independent of the original group element, except if the group element is 1, but every other group element works, because every other group element is generated. Okay, what's kind of the interesting thing about discrete logarithms, or like this group setup that we have here? What we believe is hard to compute is if I give you a group element G and a group element, and this group element raised to the power of some random x, then it should be difficult for you to compute x. Okay, so in this way I can kind of hide exponents by just giving you group element raised to the power of exponent, and then you won't be able to get back the exponent. This is something that we believe. By the way, I only say we believe this is hard because we can't prove it. Essentially, all of cryptography is built upon assumptions, which is very broadly speaking because we don't know whether P is equal to NP. Let's say P is equal to NP, then this assumption would not be true. It would not be hard to compute such an X, because then we would just throw our SAT solver or polynomial times SAT solver at this problem, and it would just output X. So all of cryptography is kind of predicated upon assumptions like this, that something is actually hard to compute. We can't actually prove it, but in practice it's actually enough that nobody is able to do it really. Like in reality, we don't know about an algorithm that would be able to do this. So it's kind of good enough in a practical sense too. The other thing that we think is hard in these groups is the following. So this was given g to the x, compute x. It's hard, you won't be able to do it. This is if I give you g to the x, and then another random group element, h, it should be hard to compute h to the x. And you can kind of imagine that this makes sense, right? Because if I just give you g to the x, because of this discrete logarithm problem, you won't be able to compute x, right? But if you want to raise this group element h to the power of x, well, you need to apply the group operation x times, but if you don't know what x is, how are you going to do it? So that's the very rough intuition why this is also probably a hard problem. So this is a new thing, right? We have something new where something may be hard to compute for the user, but easy for the provider. So we can imagine that the provider has x, this is like the provider's key, and so the provider will be able to raise random group elements to the power of x because he knows x. But if I'm the user and I only get x in the exponent of group elements, I won't be able to raise further random group elements to this power because I don't know x. And this is a cool thing because now there's new chance for us to build new crypto stuff. Let's do exactly this. We'll try to come up with a new algebraic coin, with a new coin construction from this algebraic stuff. And what we start with is just I replace what we did with the hash function with the new raising group element to the power of some hidden secret exponent. Okay, previously it was hard to compute hash values without knowing the secret key, if the secret key was part of the hash input. And now the idea is that it will be hard to raise group elements to the power of a secret exponent. Good, new approach. Kind of the old one, but like now with group stuff. The provider chooses a key k. This is the secret exponent. Now to earn points, the customer chooses a random ID for the coin, as before, sends the ID over to the provider. And now what the provider answers with, what is our new S, is the ID raised to the power of k. This is the thing that the user can't compute himself. Okay? So very simple so far. The issue is, obviously, this protocol still has no privacy because while I'm earning points, I'm sending the ID in the clear. So later when I spend the coin with this ID, provider will be able to link stuff. And there's also another issue which we'll get to next. But first, let's solve the sending the ID in the clear issue, because this is what is really cool about group stuff or discrete logarithm stuff. We can now actually hide the ID from the provider while we are earning the coin. How do we do this? New earn protocol. Customer chooses a random ID as before, but now he also chooses a random exponent r. And then instead of sending ID, he sends ID raised to the power of r. And if you remember the general group stuff that I talked about before, if I raise a group element to the power of some random power, to the power of some random exponent, then the result is just uniformly random and doesn't tell me anything about the original group element ID. Okay? So I can send this ID raised to the power of r to the provider, and the provider has no information what my ID is. Now the provider does what he always does. He takes what I'm sending and applies the key to it. In this case, raises the ID to the r that I'm sending to the power of k. And this is what we call S prime. And the customer or the user now gets this S prime. And now what he does is kind of unblinded. Okay, so this raising it to the power of r was the blinding step. And now we unblind the S prime. So here we raised it to the power of r. Here we are raising the S prime to the power of 1 over r. And this has the effect that this blinding factor r that we had here actually cancels out with the 1 over r that we are doing here. So in the end, the S that we're getting, the r cancels out, and the S that we're getting is actually just ID raised to the power of k, as we had before. But now we have this cool protocol where the provider learns nothing about the ID that is just raised to the power of k. So we can run this earn protocol without revealing the ID of the coin that we are currently earning. This would not be possible with hash stuff, because with hash functions we don't have these nice like canceling out properties, right? We can't just say I sent you some blinded value and then later I do kind of the undo operation of this blinding, and the result still makes sense. No, this with hash function this is not possible. But this is the cool stuff about like dlog and group things. All right, so this was really helpful for privacy. Let's take a look at the spend protocol. Kind of works as before. I just send over my coin and the provider checks that the ID has not been spent, and then also checks that the S is kind of the valid S for this ID. By checking that S is actually ID raised to the power of the provider's secret key K. Now the issue is this has one huge security gap, which is the customer, if he ever had a coin like this, like ID and S, he can just raise this coin to the power of 2, for example, and get a new valid coin. So this ID squared, S squared, if he sends this to the provider would see a new ID that he hasn't seen before, which is ID squared. So the database says this is a new coin, cool. And then he checks this equation, but this equation also holds because we just raised both, because we just raised the left-hand side and the right-hand side to the power of 2. Okay? So the equation still holds for this new coin. And this is really bad because now as a user I was able to take my old coin and compute a new coin with a new ID from it. And it gets even worse because I can't just do it with the power of 2, but with any power. So essentially, as soon as I have one coin, I just can compute arbitrarily many coins from this one coin. And well, obviously, as a provider, you don't want this. You want to be in control of how many coins customers have. Okay, so let's think about this. We somehow need to disable the user's ability to do this, right? To just raise the coin to some power, to get a new valid coin. And for this, the issue that we're facing is kind of that the ID and the S, they are algebraically so tightly linked, there's such a strong dependence between them that they have all of these homomorphic properties that were really convenient when we did like the earn protocol, where we did the blinding and unblinding. But now kind of get in the way, right? So what we need to do is we need to break the strong algebraic dependence between the ID and the S. And if we think about what we actually had as an assumption, then we've kind of sidestepped a little bit of this, right? The assumption was if I give you G and G to the X, and then a random group element H, then it's hard to raise this random group element to the power of X. So we only get actually guarantees if the group element H is random. Because for example, just raising G squared to the power of X, this is easy to compute. I just square the G to the X. This is the same issue that we have here too. So what we need to do is kind of make this H, the group elements that the user has to raise to the power of this unknown exponent, this needs to be a random group element. So what we're going to do is we're going to combine hashing and the group stuff, the discrete logarithms things. We've seen hashing, and we're going to take the best of both worlds, kind of. With hashing, we had this really rigid structure. So if I feed a hash function with slightly changed input, then the hash function will completely freak out and just give me a completely unrelated random output. Right? So it completely destroyed any structure in the input. If I have two related inputs, put them in the hash function, I will get two completely unrelated outputs. Groups, on the other hand, they have this nice homomorphic properties where I can do like blinding things, where I can send like a blinded version of something to the provider does something, and then I can unblind it later, and the result kind of still makes sense. This is more the group world. And now we want to combine both of those. And the idea for this is actually surprisingly simple. We'll just take the ID from the old protocol and now instead use the hash of the ID in its place. That's the combination of the two words. Okay, new end protocol. Customer chooses a random ID, which is the bit string again, and a random exponent R. Now the user sends the hash of the ID raised to the power of R. Okay. This still hides the hash of the ID, and hence also the ID, from the provider perfectly, because we've just raised a group element to the power of some random exponent. I need to say we are now interpreting hash values as group elements. The provider does what he always does. He basically takes this value and raises it to the power of his secret key k, sends back this result, which is S prime, and now the user does the unblinding again, like we had in the previous protocol, by raising it to the power of 1 over R. So if we then compute it out again, we get that S in the end is not the ID raised to the power of k anymore, but the hash of the ID raised to the power of k. And this kind of works out. The good thing is the provider can't learn anything about the ID still, because it's hidden by this blinding factor R. So this is just a uniformly random group element, doesn't tell you anything about ID. And also this is still true if he later learns the ID. So if he later learns the ID, he can compute hash of the ID, but this still doesn't tell him anything about like what this group element here, whether it has been, whether this is actually hash of the ID raised to the power of R, or the hash of some other ID raised to the power of some other R. No clue, just uniformly random. Good. Now, so we could use still the group structure and allow this blinding and unblinding. Now, if we spend a coin, we do the same thing as before. We again reveal the coin. Now the provider checks the ID again and also checks whether this equation works. So whether S is actually the hash of the ID raised to the power of k. Now this works. Now we can think about like the attack that we had before. Before we could just take the ID, raise it to some power, and then also adapt the S accordingly. This algebraic structure is now broken because of the hash function. Because if we change the ID in any way, the hash function will just give us a completely different random hash. Okay? So if we change the ID even a little bit by like squaring it, the hash will be completely unrelated to the old hash. So then if I take my S for the old hash to the power of k, I don't know how to compute the new hash raised to the power of k from that. Because, well, it's a new hash, it's a new group element, I don't know how to raise that to the power of k. This also, if you think back to our assumption, makes more sense, because now actually effectively this group element that the user wants to raise to the power of this hidden secret exponent, this is the hash of something. And this hash of something is random, because we imagine the hash to be like this, this magic box that just gives us random values. So this fits way better to our assumption that it's hard to raise random group elements to the power of a hidden exponent. Alright, and that's actually already it. This is the final construction that we have for this, or at least the final simplified construction that we have for this talk here, which kind of nicely combines the hash function and the group world, where the whole group stuff allows us to blind and unblind things, and the hash makes it so that we actually broke this algebraic dependency that made it possible for users to just come up with their own coins. All right, so to summarize, we've constructed an anonymous coin system from hash functions and discrete logarithm style groups. In the actual project, we actually don't use this approach, but you can think about our approach being more that the user holds a single coin and the coins have values. So the coin may be worth like 5 points, and then I can update the value of this coin incrementally without revealing the ID of the coin. Because the issue of the construction that we've just seen, which, well, it works, right? But the issue is that if I have 200 coins or 200 points, I also need to store 200 coins. So 200 times like the ID of the coin and the S for the coin. Need to store all of these. And in our actual project construction, we have kind of a single coin. So your storage requirements are much lower. The other thing that is kind of unfortunate about the construction simple construction that I've shown here is that the provider also always needs to be online. So if I come with a new coin that I want to spend, the provider needs to check the database whether this coin has been spent before. And if the database is offline, well, he can't check and he can't kind of take my coin. Or at least he shouldn't, because maybe I've already spent it and he won't be able to tell. What we've built into our construction is offline double spending detection, meaning that even if the database is offline, the provider can just kind of accept my coin, and we will give him cryptographic guarantees that if this coin has been spent before, then he will be able to look at the coin that has been spent twice, and will be able to find out which user is behind this coin. So in this case, anonymity would be revoked, and the provider would be able to find out who is kind of cheating the system right now. And this allows the provider even to accept coins while the database is offline. All right, thanks for watching this talk, and see you.